Assalamualaikum warahmatullahi wabarakatuh. My name is Nowo Rifeli from Department of Physics, Universitas Pajajaran, West Java, Indonesia. In this conference, I will be presenting our work with title Calculation of Quantum Harmonic Oscillator Energies using Path Integral Monte Carlo. As an introduction, I will explain what is path integral. Path integral is an alternative formulation of quantum mechanics invented by Richard Feynman in 1940s. As an alternative formulation, that means there is another approach which is the mainstream approach, particularly the one that is taught to students, especially university physics students. And that mainstream methods is the Schrödinger equations. So students are much more familiar with the Schrödinger equations and almost have no contact with the Feynman path integrals. This is unfortunate because path integral actually plays important roles in many advanced studies in physics, such as quantum field theory, solid state physics, molecular dynamics, and etc. Also, that path integral provides a more intuitive understanding on quantum mechanical systems. Therefore, it is important to provide an introduction about path integral to university students. So the goal of this study is to use path integral methods for calculations on simple mechanical system. In this case, it's the quantum harmonic oscillator. So this is the path integral formulations as derived by Richard Feynman. It's actually calculating the transition amplitude of a particle moving from x1 to xn. And it is obtained by the integration over the xt. So this xt is a path, is a function, which x is a x position as a function of t. So this is actually an expression of integration over all possible paths from x1 to xn. And the one that is integrated is the exponential of I, integral of the Lagrangian. So integral of the Lagrangians is called the action. So this is a brief description of path integral formulation. Then we have something called weak rotation, that is to rotate or to transform time into its imaginary time. That is by changing t into minus I, the imaginary number, times tau. This will give us a new expression of the path integral where there's no longer I in the exponential. This makes it possible to do numerical calculation. Okay, so that was about the path integral very briefly. Now we will talk about the quantum harmonic oscillator. So to remind us, the potential of the quantum harmonic oscillator is this: half m omega square x square. M is the mass, omega is the frequency, x is the position. And if you plug this into the Schrödinger equation, we can actually obtain the solution of the wave function as well as the energies for different states. So the ground state of the harmonic oscillator is 1/2 h bar omega. And as you go into the excited stage, you add 1 point for each excited state. So 3/2, 5/2, 7/2 h bar omega, and so on. So that is the result that we can actually derive quite easily, which we will be using as a reference to check the results from our path integral. Now this is the calculation of the energies in the framework of path integral. the ground state, we will obtain it from two-point correlation function, and also this is the method to obtain E1, energy of the first excitation value. Now the path integral Monte Carlo, which is the numerical methods to calculate the path integral. What we do is, first of all, we set up the time size or the lattice size. That is how much number of size slices in time. So that's n tau. We also determine the spacing between the time slices, which is delta tau. And then we define m and omega such that they become dimensionless, but we will use m and omega with a value 1. So that we have the harmonic oscillator action S in its discrete numerical formula with this time slices formulation. Okay, so this is the action. So you have m over 2 xi plus 1 minus x. This is the v, the velocity square, and this is the x squared, the potential. Okay, and then the algorithm of this numerical method is, first of all, we generate a random number u, and then we propose a new value to change value x to become x plus u, and then we will calculate the change in action delta s. If the new values lower the action, then we will accept this new value, because that means it has a higher weight in the probability. If you go back to the path integral formulation, while those that would increase the action, then it will be accepted with the probability of exponential minus delta s. So there will be a procedure of calling a random number to evaluate this probability. When this generating procedure are done, then we will have a number of configuration, a number of paths, where we will use those paths to calculate our observable. So in this case, for the two correlation function, for example, we will calculate xi, xj for all possible configuration. So this is the setup. We use 6 different time size and time spacing, which will give us the same value of t. There are 100,000 ensembles, that means 100,000 of different paths. So this is the result for the ground state energy. We found that as delta tau became closer to 0, it will goes to 0.5, which is the analytical value that we know. Now to calculate the first excitation energy, we will have the difference between E1, first excitation energy, minus E0, the ground state, from the slope of this formula, the dt of log G2. G2 is already defined. So for every different delta tau, we plot G2 as a function of n, then we get the slope. And this gives us this result. For the first excitation energy, it goes to somewhere close to 1.5. So it's not very similar or the same with the analytical result. Now this is the second excitation value. It's the slope of G4. And we get a result that is close to the analytical, which is 2.5. For the conclusions, we have performed path integral Monte Carlo methods to calculate the energies of quantum harmonic oscillator up to the second excited state. The results are agree with the analytical Schrödinger equation result. The implementation of these methods are executed on a typical laptop with reasonable computation time and high precision. That means these are a calculation that can be performed with standard utilities for students or anyone. Thank you. Assalamualaikum warahmatullahi wabarakatuh.